the structure of hemoglobin? Here I have shown the structure of heme group, the structural unit present in hemoglobin. If I say heme belongs to a special class of compounds called coordination compounds, what will you understand? In this class, I will introduce you to coordination compounds and some important terms pertaining to coordination compounds or coordination complexes. Coordination compounds or coordination complexes are a class of compounds in which metal atoms are bound to anions or neutral molecules. Here I have shown an example where the metal is nickel and is bound to cyanide ions. Nowadays, we call these compounds as coordination compounds. These are in fact addition compounds. That is, they are formed by the combination of two or more stable compounds in a stoichiometric ratio. However, they do not break down into individual components in water. Why is that so? In this context, it would be appropriate to understand the structure of these compounds. Alfred Werner was the first person who formulated the ideas about the structures of coordination compounds. In order to understand the structure of coordination compounds, Werner synthesized a large number of coordination compounds. Then he studied their physical as well as chemical characteristics. Based on the experimental results, Werner formulated his theory called Werner's theory. According to Werner's theory, chromium chloride has a primary valence of 3 and cobalt chloride has a primary valence of 2. This means chromium chloride and cobalt chloride gives 3 and 2 chloride ions respectively in the solution. Then what about coordination compounds? Let's understand the term valence with examples. Consider two cobalt complexes. Werner added excess silver nitrate to 1 mole of these complexes. It was found that in the case of first compound, 3 moles of silver chloride were precipitated, whereas in the case of second compound, only 2 moles of silver chloride were precipitated. Based on these observations, you may formulate the molecular formula as shown here. The atoms within the square brackets form a single entity. This does not dissociate under the reaction conditions and is described by the term secondary valence, and the ionizable group forms the primary valence. In fact, the species within the square bracket are coordination entities or complexes, and the ions outside the square bracket are called counter ions. In these examples, chloride ions are the counter ions. Usually, the central atom or ion and the ligands attached to it are enclosed in a square bracket, and they are collectively termed as coordination sphere. Thus, by Werner's theory, in coordination compounds, metals show two types of valences, primary and secondary. The primary valence are ionizable and satisfied by negative ions, whereas secondary valences are non-ionizable and they are satisfied by negative ions or neutral molecules. Also, the secondary valence is equal to the coordination number and that is fixed for a particular metal. Werner also suggested that secondary linkages to the metal have characteristic spatial arrangements which are corresponding to different coordination numbers. That is, they form polyhedra such as octahedron, tetrahedron, etc. For example, here you can see in potassium tetrachloronickelate 2, tetrachloronickelate has tetrahedral structure. Thus, the spatial arrangement of the ligand atoms which are directly attached to the central atom or ion defines a coordination polyhedra about the central atom. In potassium tetracyanonickelate 2, the coordination polyhedron is tetracyanonickelate 2. It has a square planar structure. I hope you clearly understood the definition of coordination compounds. Note that coordination compounds are not double salts. Double salts such as Mohr salt or potash alum break down into individual constituents when dissolved in water and they lose their individual properties. For example, potash alum in water will give potassium, aluminum and sulfate ions. However, complex ions do not dissociate into corresponding ions. Next, we will learn certain important terms pertaining to coordination compounds. We will start our discussion with the term coordination entity. As mentioned earlier, the coordination entity includes a central metal atom and a fixed number of ions or molecules bound to it. In potassium tetrachloronickelate 2, the tetrachloronickelate is a coordination entity, and the atom in the coordination entity to which these ions are bound in a definite geometry is called the central atom. Here, nickel is a central atom. These central atoms are also referred to as Lewis acids. These ions or molecules bound to the central atom or ion in the coordination entity are called ligands. These may be simple ions such as chloride, small molecules such as water or ammonia, larger molecules such as ethylene diamine, or even macromolecules such as proteins. Now let us see the classification of ligands. Ligands can be unidentate, bidentate and polydentate. We learn each of them with examples. Unidentate ligands are those ligands which bound to the metal ion through a single donor atom. For example, ammonia, water, carbon monoxide, etc. When a ligand can bind through two donor atoms as in ethylene diamine or oxalate, then it is said to be didentate. Here you can see ethylene diamine which binds to cobalt through two of its nitrogen atoms. When several donor atoms are present in a single ligand such as EDTA, the ligand is said to be polydentate. EDTA is ethylene diamine tetraacetate and is a hexadentate ligand. Here you can see EDTA binds to cobalt through 2 nitrogen and 4 oxygen atoms. That is, there are 6 donor atoms. Such ligands which use 2 or more donor atoms simultaneously to bind a single metal ion are said to be a chelate ligand. And number of such chelating groups is called the density of the ligand. As mentioned earlier, the bidentate ligand ethylene diamine which forms a 5-membered ring when both nitrogen atoms attach to the same metal is a chelate complex. Note, chelate complexes are more stable than similar complexes containing unidentate ligands. Next we will discuss ambidentate ligands. A ligand which has 2 different donor atoms and either of the two binds in a complex is called a ambidentate ligand. An example is nitro group which can attach to a metal atom either by nitrogen atom to give nitrito N complex or by oxygen atom to give nitrito O complex. Now we will discuss yet another important term, that is coordination number. Coordination number of the central atom is the number of sigma bonds formed by the ligand with the central atom. The pi bonds formed between the ligand and the central atom are not counted for this purpose. So here the coordination number of nickel is 4. Next, let us learn about the oxidation number of central atom. The oxidation number of a central atom in a complex is the charge it would carry if all the ligands removed along with the electron pairs that are shared with the central atom. For example, here the oxidation number of copper is +1 and is represented as Cu1, that is by a Roman numeral in parenthesis followed by the name of coordination entity. Finally, we may understand the classification of coordination compounds into homoelliptic and heteroelliptic complexes. Complexes in which a metal atom is bound to only one kind of donor groups are called homoelliptic complexes. Here you can see nickel is bound to only cyanide ions. No other ligands are present, hence this is a homoelliptic complex. Heteroelliptic complexes are those in which a metal is bound to more than one kind of donor groups. Here you can see cobalt is bound to ethylene diamine as well as chloride ligands. In this video, I have given a brief introduction about coordination compounds. Now, can you identify the coordination compounds among these? Yes, the first two belong to the class of coordination compounds, whereas nickel chloride and sodium sulfate are not coordination compounds. What will you call these coordination compounds? How will you name these coordination compounds? You will learn about the nomenclature of coordination compounds in our next video. Now, let's summarize what we have learned today.
Manorama Horizon. Learning made simple.